We're here to learn some backtracking today. One of the classic problems for backtracking is n queens. The first time I saw n queens, I was like, hell to the nah, I am not solving that. No way, that problem looks way too hard for me. I would probably never be able to solve it. And it probably took me like 2-3 years for me to even stand a chance, man. And today I'm gonna show you how I solve n queens using backtracking. So the first thing I'm gonna do is read the problem. N queens. The n queens puzzle is the problem of placing n queens on an n by n chessboard such that no two queens attack each other. Given an integer n, return all distinct solutions to the n queens puzzle. You may return the answer in any order. Each solution contains a distinct board configuration of the n queens placement, where Q and dot both indicate a queen and an empty space respectively. So here we go. This is what I like to do first. First I'm just gonna create a board, like right off the bat. So our board is just gonna be a vector string. I'll call it board. We'll initialize it to size n, and we'll put some strings in there also of size n, and I'll put like dots in the strings. So it's just gonna be a board filled with dots initially, and that means each cell is gonna be empty. So the idea behind n queens is we can't have any queens being able to attack each other, and a queen can move in like any row, infinite row, in the row direction, in the column direction, in the diagonal direction, or in the anti-diagonal direction. If you don't know what an anti-diagonal is, an anti-diagonal goes from like top right to bottom left, and a diagonal goes from like top left to bottom right. So we just gotta make sure that there's like one queen per each of those axes. All right, here we go. So how do we make sure that there's only one queen per thing? I'm gonna do that with a set. I'm gonna keep a set that keeps tracks of like all the queens in each row, column, diagonal, anti-diagonal. Here we go. Unordered set. I'm gonna call this rows. I'm gonna make 4 more of them to track my columns, the queens in the columns, the queens in the rows, the queens in the diagonals, the queens in the anti-diagonals. And I'm gonna use backtracking here, and I'll make a lambda function. I'm using a lambda function because it's a lot easier to deal with not having to pipe down your objects into the helper function. So before I learned how to use lambdas, I was using just regular functions like helper functions. And man, it's such a pain in the ass to pipe down all the variables. So lambdas is like a nice way to do that. In this thing, in our recursive function here, we only need to keep track of the row, and I'll talk about that a little bit. So how do we know when we've placed n queens? The way I'm going to implement, if we reach the end, then we've probably placed n queens. So if our row is greater than n, greater than equal to n, that means we're out of bounds, and we can add the board in its current state to the answer. Let me make my answer thing. Vector, vector, ends. So here I'm just gonna push back the board and return. That's like end conditions. So for every row that we're in, we want to iterate through all the cells in that row, all the columns in that row, and we're going to try to place a queen in each of those cells. So let's iterate through all the cells in that row, and we just want to like check if we can place the queen, and if we can, we should place it. So how do we do that? We gotta check like if the rows doesn't have this row already, and the columns also doesn't have the same column that we're in, a queen already. And what else? The diagonals and the anti-diagonals. If all of these things are true, that means we can probably place a queen there. Not probably, for sure we can. So how do you know what diagonal a thing is on? We can do that by calculating the diagonal, which is r minus c, and the anti-diagonals are r plus c. You can like fact check me and play around with those things if you want, man. So how do we place the queen? We're just gonna change that cell to a Q, and then we backtrack. So anytime we do backtracking, it's always like the same pattern, man. So backtracking is like, it takes a while to get used to and understand, but once you understand it, it's pretty easy to I guess implement sometimes, because it's always the same, man. You do something, you backtrack, and then you undo all the stuff that you just did. I'll show you what I mean right now. So when we want to place a queen, we change that cell from a dot to a Q, and that's like placing the queen. And then we do the backtrack, and we just like move on to the next row. And then after the backtrack, we undo whatever we just did. So we'll just put it back to a dot. But we also have to mark which row, column, diagonal, and stuff that the queen we just placed is in. So we'll put rows, inserts, row, calls, inserts, call, diagonal, inserts, the D, anti, inserts, A. And that's gonna make sure that we make a note of all those places where that queen is. And then we gotta like undo it after. So just erase all that stuff here. So that's like how this backtracking stuff works. What we're doing, we just go from each cell. So we try and place a queen like here. If we place one, we just move on to the next row and we do the same thing again. All right, so now we just have to call the backtracking function, and we're gonna start from row 0, and we should just be able to return the answer. And hopefully this passes, and if it passes, we're gonna talk about the time complexity. Oh man, I forgot the semicolon. Always do that, man. All right, so that's it. Not bad, not a bad problem. Scary problem at first for sure, but not too scary. So what is the time complexity? Let's talk about that. Time complexity here. So usually for backtracking problems, it's like in the order of factorial. So we can have up to n rows or cells or whatever. So the time complexity is, we're only placing one queen per row. So it'd be n factorial, I guess. I don't know if I feel comfortable talking about time complexity. I don't really know what I'm talking about sometimes. But that's the dang time complexity. Space complexity would also be like O of n. We're using, there will be at most n items in each of these things. So it's like O(n) space complexity and n factorial time complexity. So that is how I like to do backtracking. And by the way, sneak peek behind the scenes making this video, I actually had some really bad code, but I'm doing all of these videos live, and somebody in the community, very famous LeetCoder, his name is Numbers, aka Josh, number 3 LeetCoder in the world. He gave me some tips on how to implement this a little bit more cleanly. So if you don't know about Numbers, you can go check out his channel. He has some great explanations on super advanced algorithms. Anyways, that's all I gotta say.